Hi, my name is Christian Nilsson, and in this video I will show you how to apply visual kinetic analyses to obtain mechanistic information of chemical reactions. Some of these analyses use concentration against time profiles, which include the VTNA, or variable time normalization analysis, and others use reaction profiles of rate against concentration of reactant, referred to as RPKA, or reaction progress kinetic analysis. Concentration against time profiles are the most common in chemistry. They can be obtained by monitoring the reaction by NMR, IR, UV, or by simply sampling the reaction and analysing the aliquots by HPLC or GC. As such, we will first inspect the implementation of these analyses. To identify catalyst deactivation or product inhibition, we need to compare reactions started at a different point. In this example, the conditions of our standard reaction are the ones in red. So, to test for catalyst deactivation or product inhibition, we will set up another reaction with the estimated concentrations of reactants after the consumption of 0.5 molar of starting materials, for example. So in this case, 1.5 molar minus 0.5 molar is 1 molar, and likewise 1.3 molar minus 0.5 molar is 0.8 molar of B. This is shown in green. Then we will compare the reaction profiles of both reactions. In this case, we are going to monitor the concentration of B and compare the performance of both of these reactions from 0.8 molar onwards. At that point, both reactions have the same concentration of reactants, but the red reaction has 0.5 molar product, and the catalyst has already completed 50 turnovers, so it could have suffered some deactivation. In order to compare both profiles, it is necessary to shift the curves horizontally. In this case, we can shift the green curve by 3.3 hours, so the two reaction profiles have approximately 0.8 molar at the same time. It is evident that in this case both profiles are different and the red reaction is slower. That can be due to the effect of the product generated in the red reaction until that time, 0.5 molar amount, or to the catalyst being deactivated. To discern between these two possibilities, a third experiment is run. The third experiment, here in blue, has the same concentrations as the green experiment, but also has the amount of product generated by the red experiment until that moment, 0.5 molar in this case. Thus, the horizontal shift of the reaction profile allows us to compare the performance of two reactions with identical concentrations of all the species, but where the catalyst has already been working for a while. In this case, both profiles now overlay perfectly, indicating that catalyst deactivation is insignificant, and the reason for the different performance of the red and green reactions was product inhibition. To elucidate the order in any component of a reaction, we have to compare profiles with different concentrations of that component and the same concentration of all other components. In this example, red will be our standard reaction, and in the three other reactions we will change the initial concentration of A, as shown in green, concentration of B, as shown in blue, and the concentration of the catalyst, as shown in orange. To find the order in A, we're going to use the reaction with the different initial concentration of A, as shown in green, in this case using the profiles for appearance of product. We create the variable normalized timescale for the concentration of A using the formula for the VTNA, as shown in column D. The first value is 0. The second value has the VTNA formula, which is the previous value of the normalized timescale, D7, plus the concentration of A at that time, plus the concentration of A in the previous point, all divided by 2 and to the power of a constant cell, in this case B6, which is the order in A, and multiplied by the difference of time between both data points, C8 and C7. Then, we only need to extend this down and use this timescale for the comparison plot. We do the same with the green experiment, and we plot both curves together. Now, we only need to change the value of the cell B6 until we observe overlay. Clearly the curves have now crossed, and the green is above the red. Overlay was observed when the order in A was 1, and as such, this is the order of the reaction in A. We could also elucidate the order in A by monitoring the consumption of the reaction component B. The formula is identical to the one used in the previous sheet, so we modify the value of the cell B6 until we observe overlay in both curves. Again, we have found the order in A to be 1. We could also elucidate the order in A by monitoring its own consumption. But in order to compare both reaction profiles, it is necessary to shift vertically the reaction profiles until the starting point for both reactions is the same. This has been done in column F, which simply subtracts 0.4 molar from the real concentration of A. The normalization of the timescale has an identical formula to the one used in the two previous sheets, and again, by changing the value of the cell B6, we can determine the order of the reactant. Again, overlay is observed when the order in A is 1. To elucidate the order in B, we're going to use the standard reaction, as shown in red, and the blue reaction, which has the same concentrations for all of the components except for B. In this case, the formula to create the normalized timescale is the same as previously, but using the concentration of B instead of the concentration of A. This is the previous value of the normalized timescale, D7, plus the concentration of B at that time, plus the concentration of B in the previous point, all divided by 2 and powered to a constant cell, in this case B7, which represents the order in B. And this factor is multiplied by the difference of time between both data points, C8 and C7. Plotting the reaction profile using the normalized timescale for both reactions allows us to determine the order of the reactant. In this case, we're using the profile of appearance of product. To determine the order in B, we change the value of the cell B7 until overlay is observed. When the order in B is 1, the lines overlay. If we further increase this value, the lines have crossed. As such, the order in B is 1. Similarly, we can also determine the order in B using the disappearance of A. Again, this confirms that the order in B is 1. Finally, we can also determine the order in B by using the profiles of disappearance of B. But, as the two initial concentrations of B are not the same, we have to shift one of the two profiles vertically to facilitate the comparison. In this case, as the difference of initial concentrations of B is 0.2 molar, we have shifted the blue profile down by 0.2 molar, as shown in column I. Using the standard variable time normalization scale for both reaction profiles, we modify the value of cell B7, and again observe overlay when the order in B is 1. To determine the order in catalyst, we use two reactions with identical initial concentrations of reactant, but different initial concentrations of catalyst. We have used the standard variable normalization for the timescale, although, as the concentration of catalyst is constant during the entire course of the reaction, a constant variable normalization of the timescale would be enough. The formula used is the previous value of the normalized timescale, D7, plus the concentration of catalyst at that time, plus the concentration of catalyst in the previous point, all divided by 2 and powered to a constant cell, in this case B8, which represents the order in catalyst. And this factor is multiplied by the difference of time between both data points, C8 and C7. Plotting the product appearance against the normalized timescale for both reactions allows elucidation of the order in catalyst. Again, identification of overlay highlights the order in catalyst as 1. Similarly, we can use the profile for disappearance of A to confirm that the order in catalyst is 1. And finally, we can also monitor the consumption of B, again to confirm that the order in catalyst is 1. We can also use all of the profiles at the same time, and by removing the kinetic effect of all of the normalized substances, A, B, and catalyst, we can estimate the K-obs of the reaction. The formula for the variable normalization includes 3 terms, A, B, and catalyst, and is made of the previous value of the normalized timescale, D7, plus one term for the normalization of A that contains the concentration of A plus the concentration of A in the previous point divided by 2 and powered to the order in A, which is shown in the fixed cell B6. Then, the term for the normalization of B, which is concentration of B plus the previous concentration of B divided by 2 to the power of the fixed cell B7, which represents the order in B. And finally, the term for the normalization of the timescale by the concentration of catalyst, which is calculated by the concentration of catalyst plus the previous concentration divided by 2 to the power of the fixed cell B8, representing the order in catalyst. This is all multiplied by the difference in time between the current and previous data point. By using this total normalization with respect to the concentration of A, B, and the catalyst for the 4 reactions, we can estimate the K-ohms. Setting up the correct order in A, the red and green profiles with different initial concentration of A overlay, but not the blue or the orange. Also choosing the correct order in B, as previously determined to be 1, the blue, red, and green profiles overlay. Also, all the profiles now become straight as a consequence of the fact that we have removed from the reaction profiles the kinetic effect of all of the kinetic driving forces changing during the course of the reaction, namely the concentrations of A and B. Finally, if we also set up the correct order in catalyst, as previously determined to be 1, all profiles now overlay on a single straight line, in which the slope of this line is approximately equal to the K-ohms of the reaction, in this case 34.7 molar to the minus 2 per hour. The same treatment can be done using the profiles of disappearance of A, with the only precaution of shifting vertically the profiles so all start at the same point. In this case, we have shifted the profile of the green reaction up by 0.4 molar, as shown in column O. Again, by setting up the correct orders in A, B, and catalyst, all reaction profiles overlay in a single straight line where the slope is approximately equal to the negative K-ohms of the reaction. Also, the concentration profiles of disappearance of B can be used by vertically shifting down the profile of the blue reaction, as shown in column U, so all the profiles start at the same point. Setting up the orders in A, B, and catalyst, as previously determined to be 1, causes all the profiles to overlay on a straight line, with the slope approximately being equal to the negative K-ohms of the reaction. Now, we are going to see how to apply reaction progress kinetic analysis, or RPKA. The main difference between the previous analysis and this one is that RPKA requires high-quality rate data, usually acquired by calorimetry. As before, we will first see how to find out if there is significant catalyst deactivation or product inhibition. To do so, we will use reactions started at different points, referred to in the literature as same excess experiments, because the difference in concentration between the reactants is the same in both reactions. In this case, the green reaction emulates the conditions of the red reaction after the consumption of 0.5 molar of reactants, but without the product that the red reaction would have generated till that moment, and with fresh catalyst. The blue reaction is the same as the green one, but now includes the product generated in the red reaction after consumption of 0.5 molar of starting materials. As we're analysing the reaction by RPKA, now the plots are rate against concentration of one of the reactants, in this case B. If you're not familiar with these plots, notice that they should be read from the right to the left. As the reactant is consumed, the rate of reaction usually decreases. By comparing the red and green reactions, it is easy to see that both reactions have different rates for the same concentration of B, and implicitly also the same concentration of A. This fact suggests that there is product inhibition or significant catalyst deactivation. The comparison of the reaction profiles of the blue and red reactions, which have the same concentration of reactants and product from 0.8 molar of B to the end of the reaction, shows two overlaid curves. Therefore, we can conclude that the higher rate observed in the green reaction was indeed a consequence of product inhibition, and there is no significant catalyst deactivation. To find out the order of reaction in reactants and catalyst, we have chosen the same reactions that we have used for the VTNA in the previous Excel file. As explained before, the difference is that now we are going to use rate profiles instead of temporal concentration profiles. We can elucidate the order in A by using the red and green experiments. To do so, we need to create a new column for both reactions with rate divided by A to the power of order in A. The formula in column G is the rate at that moment, F8, divided by the concentration of A, D8, to the power of B6 as a fixed cell, which will be the order in A. We do the same for the green reaction in column L, and then these two columns are plotted against the concentration of B. Then, the value for the order in A is modified until both curves overlay. As such, the correct order in A is 1. The order in A can also be elucidated by using the red and blue reactions. Although these two experiments have the same initial concentration of A and different initial concentration of B, part of their reaction profiles can be compared to obtain the order in A. In particular, after the consumption of 0.2 mol of the reactants, the blue reaction will have the same concentration of B, 0.6 molar, and different concentration of A, 1 molar in the case of the red reaction, and 0.8 molar in the case of the blue reaction. Therefore, these sections of the reaction profiles can be used to elucidate the order in A, if we are sure that there is no product inhibition and no significant catalyst deactivation. Changing the value of the cell B6, it becomes clear that the profiles can be compared for concentrations of B that are smaller than 0.6 molar and the order in A is 1. To find the order in B, it is necessary to compare reaction profiles from the moment when the concentration of A is the same, but the concentration of B is different. In the case of the red and blue reactions, the starting concentrations already satisfy this condition, so the entire reaction profiles can be used to elucidate the order in B. As we want to determine the order in B, the y-axis will now be rate divided by the concentration of B to the power of the order in B, in this case the fixed cell B7. Then, this column is plotted against the concentration of A. By changing the value of the cell B7, we can find that the order in B is 1. As the total amount of A consumed in each reaction is different, only the section of reaction between 1 and 0.4 molar of A can be compared. Order in B may also be elucidated by using the red and green reactions. In this case, the sections of the reaction profiles valid for the comparison are between 0.6 molar and 0.4 molar of A, as both reactions can only be compared with the same concentration of A and different concentrations of B. As mentioned previously, this comparison between reaction profiles that does not correspond to the starting conditions of the reaction is only valid if there is no product inhibition or catalyst deactivation. Modifying the cell B7, again, it can be seen that the correct order of B is 1. This is a small section to discern overlay, and so obviously comparison of larger sections of reaction profiles is more adequate. So in this case, the use of the blue and red profiles, as previously discussed, would be recommended. To find the order in catalyst, we use the orange and red reactions, set up with different concentrations of catalyst. In this case, the rate must be normalized by the concentration of catalyst powered to the correct order in catalyst, as shown in cell B8. This normalized rate can now be analyzed against the concentration of B by changing the value of this cell. As shown, it is clear that the reaction is order 1 in catalyst. Similarly, we can elucidate the order in catalyst by plotting the normalized rate against the concentration of A. Again, this confirms that the reaction is order 1 in catalyst. Finally, the K-obs of the reaction can be estimated by normalizing the rate of the reaction by all of the components of the reaction minus one of the reactants, which is plotted in the x-axis. In this case, we are normalizing the rate of each reaction by the concentration of A and catalyst to their correct orders of reaction. And plotting it against the concentration of B to the correct order in B, as previously determined to be 1. If all of the orders of reactions are correct, and the effect of all of the components with a kinetic effect on the reaction rate are considered, all of the reaction profiles overlay on a straight line, which slope is approximately the k-obs of the reaction. This is the end of the video, where we first covered the visual kinetic analysis of profiles plotting concentration against time, and then profiles of rate against concentration of reactant. We hope this video has been useful to you. Of course, if you have any questions, please don't hesitate to contact us, and thank you very much for watching.